Welcome to the online lecture on Signals and System. Myself Harsha A, Assistant Professor, Department of Electronics and Communication Engineering. Today I am going to take the topic discrete time Fourier series representation of periodic signals, that is DTFS. The topic which I like to cover is derivation for expression of DTFS and expression for DTFS coefficient, need for DTFS, why we want to go for studying DTFS, and some problems associated with DTFS and convergence of DTFS and its properties. Okay, first we will start with expression for DTFS from the topic that we studied in the last session from CTFS, that is continuous time Fourier series. Okay, let us start with CTFS. We know that CTFS, that is continuous time Fourier series. This is we have written for signal x of t, and we are assuming that the signal x of t is periodic in nature, that is x of t is periodic. So, signal x of t is periodic means x of t plus capital T is equal to x of t, and we are assuming that the fundamental period is capital T, and we can represent the continuous time Fourier series representation for x of t as x of t is equal to sigma Ck e raised to j k omega naught t, where k varies from minus infinity to plus infinity if it is a both sided Fourier series representation. So, this is a general expression or it is for both sides. If you are interested for a one sided Fourier series representation, your sigma will range from k varies from 0 to infinity Ck e raised to j k omega naught t, where Ck we call it as the Fourier series coefficient, that is Ck is CTFS coefficient. So, the need for CTFS is that you are representing a signal x of t as a summation of periodic signals e raised to j k omega naught t with fundamental frequency omega naught, and the expression for fundamental frequency omega naught is 2 pi by capital T. So, we will move to the next session how we can see the periodic signals or how will you represent the periodic signals. So, we can look into the signal x of t. This is a periodic, an example for a signal which is periodic with period capital T. The corresponding fundamental frequency omega naught is equal to 2 pi by t. Suppose we are going to sample the signal x of t at the corresponding sampling rate according to the Nyquist criteria. So, the corresponding sampled signal that we obtained is drawn here. So, you will get the discrete signal x of n corresponding to x of t with period capital N, and the corresponding fundamental frequency is omega naught is equal to 2 pi by capital N. Now, we know the expression for Fourier series expansion of x of t. Now, I am going to change the Fourier series expansion of its discretized version x of n. So, we know that I am rubbing this one. So, we know that the expression for Fourier series expansion is x of t is equal to sigma Ck e raised to j k omega naught t. Suppose I am taking the general formula, my k is varying from minus infinity to infinity. Here my period is t is my T is my fundamental period capital T is my fundamental period with fundamental frequency omega naught is equal to 2 pi by T. So, I am going to change this expression. T will change to capital N and my omega naught will change to 2 pi by N. So, I am going to substitute these two conditions in equation number 1. So, I will get the expression for Fourier series is x of n is equal to sigma k varies from minus infinity to infinity, but Ck will remains the same, e raised to j k instead of omega naught, instead of t it will come the variable n. Now, I am going to substitute my omega naught is equal to 2 pi by n in this expression. I will get it as, I am going to rub this part. So, I am going to get the expression as x of n is equal to k varies from minus infinity to infinity Ck e raised to j k 2 pi by n into small n. Let us assume this e raised to j k 2 pi by n as an another variable, say phi k. Let phi k is equal to e raised to j k 2 pi by n into n. Suppose I am interested to calculate the values phi 1, phi 2 etc. by substituting value for k is equal to 1, 2, 3. I will get it as phi 1 is equal to e raised to j 2 pi n by capital N. This is also equal to e raised to j 2 pi n by capital N plus 1 plus n, because when you open this expression we will get it as e raised to j 2 pi n by capital N into e raised to j 2 pi n, because these n and n will cut out and the value of this one is 1. So, you will get the value as same as this one. So, phi 1 is equal to this one. Similarly, I am able to write it as phi 2 is also equal to e raised to j 4 pi n by n, that is also equal to e raised to j 2 pi by n into n plus 2n. So, we can understand the thing is that your k is not varying from minus infinity to plus infinity, because this one is also seemed to be periodic, that is this one is also periodic over an interval. This one is also periodic for an interval n. So, that means this expression your k is not varying from minus infinity to infinity, this is varying from either 0 to n minus 1 or minus n by 2 to plus n by 2. Okay. So, this one is also periodic. So, I am able to write the expression as my k is varying from over an interval of n Ck e raised to j 2 pi k n by capital N. So, this is the expression for dtfs. So, this is the expression for dtfs. Now we will find the where Ck is the DTFS coefficient, where Ck is the DTFS coefficient. Now we will derive the expression for Ck. To find the expression for Ck, we will start from this equation onwards. So write this equation as equation number 2. So we will start from this equation. So multiply this equation on both sides by a variable of e raised to minus j 2 pi r n by capital N on both sides into this one into x of n is equal to sigma k over n Ck e raised to j k 2 pi n by capital N into e raised to minus j 2 pi r n by capital N. Then apply sigma on both sides. We will get sigma x of n e raised to minus j 2 pi r n by capital N is equal to sigma r varies over an interval n, sigma k varies over an interval n, Ck e raised to j 2 pi by n we can take an outside. So k minus r into n. We can club this exponential together and taking the e raised to j 2 pi by n common outside, we will get the expression like this. Then when you are looking on the right hand side of the expression, this k variation is only for the Ck. So we can change the order of integration, there is no problem. Change the order of summation. So I am changing the order of summation, taken the sigma k outside and sigma r inside. We will get sigma x of n e raised to minus j 2 pi r n by capital N, r varies over an interval of n, equal to sigma. I am changing the order of summation. So first I am writing the order for k, summation for k, Ck, then sigma r varies over an interval n, then e raised to j 2 pi by n k minus r into n. So looking into the rightmost term, we can understand that this expression is equal to 1 for if k is equal to r or k minus r is an integer multiple of in these two cases this expression will become 1, otherwise this expression will become 0, otherwise this expression will become 0 for k not equal to r. So I am taking the condition, the first one, assume that your k is equal to r. So this expression will become sigma k varies over an interval of n, sigma Ck R varies over an interval of n, this one is equal to 1. So, when you sum this one and we are taking the condition that k is equal to R. So, applying this condition here, your k is not varying from over an interval n, your k is equal to R. So, this will become CR. So, this expression will become CR and this summation will equal to n. And your left hand side is sigma R varies over an interval of n, x of n e raised to minus j 2 pi r n by capital N. Then taking this n to this side, you will get the expression as CR is equal to 1 by n sigma R varies over an interval of n, x of n e raised to minus j 2 pi r n by capital N. So, this is the expression for DTFS coefficient. So, combine together once more I will write the expression for DTFS and its coefficient. So, expression for DTFS is a signal x of n whose DTFS is x of n is equal to sigma Ck e raised to j k omega naught n k varies over an interval of n, where Ck is the DTFS coefficient and the expression for Ck is 1 by n sigma k varies over an interval of n x of n e raised to minus j k omega naught n, where your omega naught is equal to 2 pi by n, and we are applying the condition that your x of n is periodic for an interval of n. So, this is the overview, that is a signal x of n which is periodic with an interval of capital N. The DTFS representation of x of n is this one, that is x of n you are able to write it as summation of signals with harmonically related frequencies with omega naught is equal to 2 pi by n, where Ck is the Fourier series coefficient and the expression for Fourier series coefficient is 1 by n sigma k over an interval n x of n e raised to minus j k omega naught n. And what is the point of doing this DTFS is that first we studied that CTFS, that is continuous time Fourier series coefficient, that is when you are designing a system. We are already discussed in our class that why we are interested in going for Fourier series is that in a system, if you are giving a signal x of t, we are finding the Fourier series coefficient. So, we will get infinite number of Fourier series coefficient and parallel processing of the signal is possible. But when you are looking into the expression for x of t, this one is infinity, but we are not able to design a system with infinite number of coefficient. So, that is why we are interested in sampling the signal, convert that into x of n and find the Fourier series coefficient of or Fourier series expansion of x of n. So, you are able to design a finite processing digital system for calculation of Fourier series and representation of signals. So, this is for today's session. We discussed about continuous time Fourier series. From that, after sampling, we are converting into digital signals and representation of digital signals using is Fourier series representation and the expression for coefficient and what is the need. because when you are designing system we need the digital representation of Fourier series and the need for that is also explained. So, today's session is over. Thank you.